Welcome back to another explainer. Today, we're diving straight into the incredible hidden engineering inside high-performance liquid chromatography equipment, or HPLC for short. You know, if you've ever walked past one of these machines in a lab, it just looks like this quiet, unassuming metal box. But under the hood, it is managing fluid dynamics that are, frankly, mind-boggling. We're going to focus right on the absolute heart of this system, the pumps, and the downright ingenious ways engineers have tackled the massive mechanical hurdles of pushing liquids through packed columns. So let's set the stage with the sheer physical stakes here. Why exactly do we need such complex pumps in the first place? Well, the stationary phase, that packing material inside the column doing the actual separation, is incredibly compact. And forcing a liquid mobile phase through that dense material creates a massive pressure drop. We're talking about back pressures that can hit a staggering 20,000 kilopascals. To put that into perspective, that's hundreds of times normal atmospheric pressure just sitting right there on your lab bench. It's absolutely wild. Think about the overall geography of the system. The flow path starts with the solvents up top, passes through a degassing system, and then hits the pump. This pump is literally the heart of the entire operation. It's relentlessly driving that mobile phase into the injector, through the thermostated column, and finally out to the detector. Everything downstream entirely relies on this pump delivering a perfectly stable, continuous flow, completely fighting against that immense back pressure from the column.
Section 1. The enemy within. Gases and bubbles.
You see, before the solvent even gets to the pump, engineers have to battle these invisible enemies lurking right inside the liquid. I'm talking about ambient gases, like nitrogen and oxygen, that naturally dissolve in our solvents. If we don't get rid of these, they will wreak absolute havoc. Under extreme pressure changes, they mess with the liquid's compressibility and form dangerous physical bubbles. And believe me, a bubble inside a high-pressure pump or detector, that will completely ruin your flow rate and your data. Plus, dissolved oxygen specifically interferes with electrochemical detection methods and can chemically degrade the stationary phase, which drastically shortens the lifetime of your very expensive column. So, to prep the liquid and dodge this multi-level disaster, the system uses some intense degassing methods right off the bat. You'll often find the solvent being blasted with ultrasound to literally force the gases out. Or they use a process called sparging, where helium is rapidly bubbled through the solvent to strip away that pesky dissolved oxygen and nitrogen. Sometimes the system will just pull the solvent through a specialized filtration membrane. The ultimate goal here is super simple: feed the pump purely liquid with no hidden gases allowed.
Section 2. Engineering for extremes. Tough materials.
Okay, so now we have perfectly degassed solvent, but how on earth does the pump survive this highly pressurized, highly corrosive environment? You have to keep in mind that corrosion effects actually multiply under extreme pressure. Standard metals just won't cut it for the critical moving parts inside. Instead, the pump's pistons and check valves, the parts constantly grinding and sealing against that mobile phase, are forged from incredibly inert, super hard materials. We're talking about components carved out of pure sapphire, sealed with Teflon, or machined from highly specialized alloys. It is extreme engineering for an extreme environment.
Section 3. The pulsation problem.
Even with those indestructible materials, there's a massive mechanical flaw with a standard single piston pump. It acts almost exactly like a syringe, right? You pull the plunger back to fill it, then you push to deliver. But this alternating action inevitably creates violent variations and pulsations in the flow rate. And in chromatography, where flow stability is literally everything, a pulsating flow is totally unacceptable. To solve that, the majority of modern HPLC instruments use a two-piston arrangement. With a serial setup, the flow rate normalizes beautifully, taking those violent peaks and valleys and flattening them right out. Let's break down this mechanical ballet step by step. First up, piston A, which is either larger in diameter or travels a greater distance, draws in the solvent and pushes it forward. But here's the clever part. It pushes twice the volume of the second piston, piston B. So part of piston A's flow goes straight into the column, while the rest fills up piston B. Then, the real magic happens. While piston A pulls back to refill, piston B pushes its stored volume into the column. By perfectly coordinating these alternating strokes, usually controlled by a motorized speed regulator, the pump elegantly regulates the nominal flow. It smooths out the bumps into a perfectly steady stream. But, of course, engineers don't leave anything to chance. To guarantee absolute perfection, many systems also throw in a pulsation damper between the pump and the injector. You can think of it like a mechanical shock absorber. The simplest design is literally just a long coil of tubing with a low cross-section.
When a tiny pressure wave hits it, the physical tube actually uncoils slightly. That tiny mechanical movement increases its internal volume just enough to swallow the pressure spike, completely dampening any leftover variations.
Section 4. Mastering the mix. Gradient elution. Now, if our mobile phase has a fixed composition, what we call isocratic mode, a single pump setup is totally fine. But what happens when our chemistry demands that the composition of the mobile phase changes over time? That's a process known as gradient elution. Well, one way to handle this is with a low-pressure gradient. Here, electronically activated proportional valves pull exactly what's needed from solvent A and solvent B. They perfectly mix these solvents in a low-pressure chamber first. But to hit the exact desired composition at a specific pressure, the instrument actually has to dynamically compensate for differences in solvent compressibility before this precise mix is blasted into the column by the high-pressure pump. Alternatively, we can use a high-pressure arrangement. This method is way more hardware-intensive because it demands a dedicated, independent high-pressure pump for every single solvent. So if you have two solvents, you're running two complete high-pressure pump systems at the exact same time. The flow controller dynamically adjusts the speed of each pump. The solvents are pumped individually at those crazy 20,000 kilopascals and then violently mixed together in a high-pressure tea just milliseconds before they enter the column.
It is truly fascinating to think about the relentless physics happening completely out of sight. None of this separation would be possible without the sheer mechanical mastery of these pumps, battling microscopic bubbles, utilizing pure sapphire pistons, and executing these precise mechanical ballets at hundreds of times atmospheric pressure. So next time you look at a chromatography result, maybe from a medical lab test, ask yourself, what immense invisible forces and extreme pressures had to be tamed just to achieve a single perfect drop of flow?